Assalamu alaikum. Today we'll continue chapter 20, which is about power. And in this lecture, we'll talk about the power triangle and the total P, Q, and S, active and reactive and apparent power. And finally, we'll conclude this chapter and our lecture by power factor, talking about power factor correction. Power triangle, we can see here the power triangle for the power in x, active power in x-axis and reactive power in y-axis, and then the apparent power, the summation between them, similar to Pythagoras. It will be p square plus q square equal s square. This formula by vector form, okay, can be related in the vector domain by s plus b equal p plus q. Okay, each terminal here by vector. P with the angle 0, QL with angle 90, QC with angle minus 90. You can see here the power diagram is called power diagram. For inductive load, it is plus 90, and for the capacitive load, minus 90. Okay, so you can see here by vector P plus J QL, and here for capacitor P minus J Q C. For example, if we have in the same network capacitor and inductor, you can add them. If it's the QL bigger than QC, the quantity will be in the positive, in the plus 90. If the QC more than QL, the power triangle will be in the negative. You can say Q total equal QL minus QC. Finally, you can say I square, if you derive the formula, I square equal XL minus XC. As I mentioned, for magnitude, you can say S square equal P square plus Q square. You can find any, if you have two of them, you can find the third one by this formula. Also, we can calculate apparent power by formula V multiplied by I conjugate. What is I conjugate? It is the same current but with a different sign, opposite sign. For example, if we have this circuit, voltage 10 volt with angle 0, resistor 3 ohm, inductor 4 ohm, we can find the current. It will be 2 ampere with angle minus 53. Okay, and then find the power, active power, I square multiplied by R, 2 ampere square multiplied by 3 will be 12 watt, and the Q will be I square by XL, it will be 16 watt. The S, it will be 12 plus J 16. Okay, and the by phasor form, you can write it 20 volt ampere 53.13. This is one way to find apparent power. Another way to use this formula Okay, if you use this formula, you will say V multiplied by I conjugate direct 10 multiplied by 2, the opposite angle in the current. We found the current by minus, but by this formula we will use the opposite. If we found the current here positive, we will use it here minus. Okay, the conjugate means the opposite side. You will find the answer 20 volt ampere angle 53, similar to this. And we mentioned before in last section, we said power factor, we can say it is P over S. If I ask you to draw the power triangle, this power triangle, okay. Now we need to talk about the total active, reactive, and apparent power. We have some tips here. We need to follow these tips. Find the real power and reactive power for each branch of the circuit, the first step. The total real power of the system is the sum of the average power delivered to each branch. Okay, we found for circuit, for example, series and parallel, and we have resistor in series branch and parallel branch. Any where the resistor, you find the total, you find the active power for each resistor and add them. You will get the total power, active power. For the total reactive power is the difference between the reactive power of the inductive load and that of the capacitive load, as we mentioned before. Then the total apparent power is total equal, we can find it by this formula. Be sure to find the total power active and add with the total reactive power. Don't find the apparent power for each load alone. If you have, for example, 7 branch, don't find the S for each branch alone and then add them. You will get the wrong answer. You need to find the total power for all the 7 branch, for example, and then the total reactive power for all the 7 branches together, and then calculate the total apparent power. After that, to find the total power factor, you divide P total over S total. Let's see this example. It will be clear here. Find the total number of watt, volt ampere reactive and volt ampere and power factor for the network figure 20.21. Draw the power triangle and find the current phasor form. Okay, we have here circuit with 2 parallel load and 1 series. Okay, we have here watt only, no var, and here we have var and watt, but the var for inductor L, and here var and watt and var for capacitor. We can write it here, the load 1, load 2, load 3, 200, 500, 200, 200, 500, 200 watt. Okay, and for the var, for the first load 0, and second load 1200, third one 900. The total var here and the total active power, we can find the total apparent power. We add them here, we found 900 watt, and we have QL minus QC, you will get 300 watt, var, and make square for each of them and add, make root, you will get 948 volt ampere. But if you find S for each load alone, this is the apparent power for the load 1. This is apparent power for load 2. Apparent power for load 3. If you add them, you will get different answer, which is wrong. This is wrong. Okay, this is right. The right one is 948. Be careful when you calculate the apparent power. This is a way how to calculate the apparent power. Find the total active power and the total reactive power, add them and make the square and root. You will get the total apparent power. After we found total apparent power and we have total active power, we can divide them. You will get 0.949. You must write lagging or leading. If you have inductive load QL more than capacitive load, you say lagging. If the capacitive load more than inductive load, you will say leading. Okay. After we found power factor, we can find now the current. S equal V by I, and we know that the V equal 120 with angle 0. You will get the current 7.91. And because the load is lagging, we can find the angle, and we put it by minus because it is lagging, and the voltage start from 0 and the current lagging by 18 degree. This means it is minus 18. For example 20.4, try to go through similar idea. Okay, go step by step. I will go with you example 20.5. okay, it has some idea. Find the average power, apparent power, reactive power for each branch. We have different type of load here, and we need to find active and reactive and apparent, total apparent power. Okay, for load 1, we have 12 bulb, each bulb 60 watt. This means 12 by 60, you will get 720 watt. No reactive power, this means Q1 is 0. And to find S1, which is equal P1, because the Q is 0, and the power factor 1 because the load is resistive load. Okay, for Q2, it is heating element. The resistor 6.4 kilowatt, sorry, power, active power 6.4 kilowatt. Okay, it is given P2 equal 6.4 kilowatt, and reactive power is 0. No reactive power, heating element always resistive load. Okay, and S2 will be 6.4 kilovolt ampere, and power factor is 1. Now to find the active and reactive power for the load 3, which is motor, we have the 5 horsepower and power factor, and efficiency equal 82%. When you see 5 horsepower in the motor, you know that this power it is output power, because we know that the motor, the input power electrical, the output power mechanical. Once it is horsepower, this means mechanical, means output. And we know the efficiency formula equal output divided by input. Efficiency, it is output divided by input. To find the input, you need to divide the output by efficiency. You will multiply 5 by 746, to convert the 5 horsepower to watt, and then divide by 0.82, you will get 4548 watt. Okay, and the power factor is 0.72 lagging. It is given in the question. Now we can calculate apparent power by dividing active power by power factor. You will get 6317 volt ampere. And by finding the cosine inverse for power factor, you will get the angle, and then you can calculate the reactive power for this load. Okay. Finally, for capacitive load, we have the impedance, we have for the voltage, we can divide by the current, and if you have the current, you can find the active power by I square multiplied by R, and reactive power by I square multiplied by XC. You will get active power here and reactive power here. Okay, then you can find apparent power by this formula. Okay, if we have active power and apparent power, you can find the power factor. It's leading because capacitive load. For part B, we need to find the total active power, total reactive power. I see here B1 plus B2 plus B3 plus B4. You will get 13,400 watt. And for reactive power, we have Q1, Q2, Q3, Q4. It's written plus minus, depend. If it is active inductor, you put it in the positive. If it is capacitive, you put it by minus, like here positive and here negative. Q3, Q4, Q1 and Q2 0, and then this is the total Q total. Now, when we have B total and Q total, you can calculate the apparent power and the total power factor for this network. You will find it 0.988 lagging, because the lagging because the inductive load more than the capacitive load in this network. For part C, it means you find the source current. Now, to find the source current, we have total apparent power and we have the voltage. We can divide them, and we know that the system is lagging. Then we can write the angle by minus 8.89. Okay, this is the angle, and because it is lagging system, we can write it minus, because the voltage angle is 0. If you remember, see in the circuit, voltage is 0, and the current lagging, it must be by minus 8. For example 20.6, try to go through. It's an easy example. Now we'll talk about power factor correction. If we have more reactive power in the system, the current will be increased. And if the current increased, why the current increased if we have more reactive power? Because the apparent power will increase. You see here the blue one for Q, the first Q is the Q small and the apparent power small. If we increase the reactive power up to here, the apparent power increased. And if we increase the apparent power and the voltage fixed, this means the current increased. And if the current increased, the result increased the power losses. Okay, since it is I square multiplied by R. And heavier current also required larger conductor, increasing the amount of copper needed for the system, and also increasing the generating capacity by the utility company. We need to generate more for the same load. Okay. Minimum current. If you have any system, you need to find the minimum current you need to reach unity power factor. This means apparent power equal active power, and reactive power is 0. Okay. And how to reduce the reactive power, since most of the load is inductive load in the factory or in the networks. We need to add something, introduce reactive element to bring the power factor close to unity. This process called power factor correction. Okay. And normally we will add a capacitor, and we will call it capacitor bank. Okay, like here, this is our load. For example, motor, it has resistor and inductor, and if we add capacitor in parallel with the load, we will reduce the reactive power from top one to blue one. Okay. And if we reduce the improve the power factor by reducing the reactive power, this means apparent power reduced. If we reduce the apparent power, this means reducing the current. Okay, and this is our goal. You can see here in this table, this one, this picture show power factor correction panel. Okay, and we have some penalties if we if the power factor reduce. We need to keep the power factor as much as we can near to 1. For example, some depend on the company and the country, but here this table shows that if the power factor from 1 to 0.9, no penalty, and if it is reduced to less than 0.9 up to 0.85, there is some penalties. Okay, and the penalties increased when the power factor decreased. Okay. Let us see some example how to solve the problem. For example 20.7, we have A, B, C, D, E parts, and some parts has mistake. Okay, typing mistake. I need from you to solve example 20.7. The first 3 students send the correct answer. I will give them a bonus. Okay, try to find maybe the mistake in A or B or C or D. I need from you, after you finish your study, try to find where is the mistake and correct them, and send me the solution, full solution from A to E by email. Okay, I will solve 20.8. 20.8 said 5 horsepower motor with the 0.6 lagging power factor and efficiency 92% is connected to 208 volt 60 Hz supply. Establish the power triangle for the load. This means we need to find the active, reactive, apparent power. We know that we mentioned that 1 horsepower equals 746. To convert 5 horsepower, we multiply by 746. You will get by what is the output, and we have the output and efficiency divided by each other. You will get I power input, which is electrical power, 4054 watt. Okay, and now we have power factor 0.6. You can find the angle. If you have the angle, you can find from the power triangle tan theta equal Q over P. Q over P, and we have P and we have the theta. We can calculate QL. QL, if we substitute, you will get 5405 var. Okay, and then we can find the S, apparent power. Now we found all the type of power. We can draw the power triangle PQS. For part B, determine the power factor capacitor that must be placed in the parallel with the load to raise the power factor to unity. We need to find the remove the Q at all to reach the unity power factor. This mean we need to cancel a reactive power. Now we can assume that the reactive power here 5405. We need to replace the by same value for capacitive load. Okay, if we replace the same quantity QC, we will get the new XC 8 ohm. Okay, and if we find the impedance, now we can say the capacitance 1 over 2 pi fxc. You will get the farad. We need to put 8 ohm capacitive load in parallel with the load to get unity power factor. Okay, for part C, determine the change in the supply current from uncompensated to compensated system. Okay, let us see here. The first we found that the apparent power 6757. We divide by 208. You will get the current 32. Okay, the new one will be the reactive power 0. This means the apparent power will be exactly the same as active power. This means we will divide 4054 by 208. You will get 19 ampere. Okay, the reduction was 40% when we add the capacitor 8 ohm. Okay, for 20.9 example, this is the last example in this chapter. Okay, say a small industrial plant has a 10 kilowatt heating load and 20 kilovolt ampere inductive load. We have two load in parallel, one heating element, one inductive load, to a bank of induction motor. The heating element mean bank of induction motor. This means many motors together. The load to 20 kilovolt ampere. The heating element consider pure resistive and the power factor 1, and the induction has lagging power factor 0.7. The supply voltage 1060 Hz. Determine the capacitive element required to raise the power factor 0.95. Also compare the level of current drawn from the supply after we find the answer. We need to correct the power factor to 0.95 and then calculate the new current. Okay, S equal V by I, which is 20 kilovolt ampere for induction motor. Okay, and to find P equal S multiplied by cosine. We have the power factor 0.7 here, multiplied by S. You will get the active power for induction motor is 14 kilowatt. Okay, and theta will be 45. Now we can substitute theta and sine and multiply by apparent power. You will get reactive power. Now we have reactive power, active power, and we have apparent power for induction motor. Okay. Now, if we need to find the total apparent power, we need to find the total reactive power and total apparent power. Total reactive power come only from motor. This means we can write the same answer, 14.28 kilovolt ampere. And active power 24. From where comes 24 kilowatt? It came from 14 kilowatt plus 10 kilowatt, because we said that if we need to find the total active power, we need to add all the active power in the system. And we have 10 kilowatt and 14 kilowatt. We add them, we get 24. Now we found the total reactive power. Please, my student, try to use your calculator to practice about these examples. Okay. And now we have apparent power divided by voltage. You will get the current in the normal situation for this system. Okay. To improve power factor to 0.95, we find theta by cosine inverse power factor, new power factor. You will get the theta 18.91. To find the Q reactive power, you will find it by this formula, P total equal tan theta. It becomes a 7.8. The new one, if we correct the power factor to 0.95, the new reactive power will become 7.9 kilowatt. Okay. This means we need to reduce the old power factor by how to find the value of reduction. We will see the old reactive power minus new one, the old one minus new one. You will get the value of the value we need to reduce. We need to reduce the reactive power by 6.38 kilowatt. This is the value of reduction. This means we need to put capacitor bank give us value of 6.38 kilowatt to reduce this quantity. See here the formula, Q equal QC E square divided by XC. Okay, XC equal E square divided by QC, and then you'll apply this formula. You will find that XC 156.47 ohm. Okay, and we can calculate the capacitance. This is the value, but we need to add capacitor bank by value of 156 to get power factor 0.95. Okay. Now we need to calculate the apparent power. If we have the new reactive power, you will get 25.27 kilovolt ampere. And to find the current, we divide active apparent power by the voltage. You will get the current. The old current was 27, and when we improve the power factor, we reach 25.27 ampere. Okay. By this, we conclude our chapter and our lecture. Wish you all best.